To understand modern electric vehicles, we have to look back to cars like the GM EV1. It was the first mass-produced electric vehicle, created by General Motors in the 1990s. These early cars started a transition that turned vehicles from mechanical machines into drivable computers. Today, we are building a mental map of how these computers work, tracing the energy's path across 5 core components. But first, clear your mental canvas. Erase the spark plugs, gears, and gas tank. None of that applies here. Building this new map transforms you from a passive driver into an informed owner. Once you know exactly how the energy flows, you can decode the marketing jargon and understand what kind of maintenance your car actually requires. We begin with component 1, the charging intake. This is where the vehicle pulls raw electrical power from either a standard home grid or a specialized public fast charging station. At a public station, you initiate DC fast charging, a continuous flow of electricity allowing the battery to accept massive amounts of energy quickly. But at 80%, charging drops to a trickle. This throttle protects the battery's chemistry from overheating. Inside the car, the energy moves to component 2, the battery pack. In a gas car, fuel sits in a compact tank tucked near the rear axle. You need to picture something entirely different here. Electric cars use a skateboard design. A flat lithium-ion battery pack is mounted at the chassis floor, lowering the center of gravity to keep the car planted through turns. This vault requires an active thermal cooling system, pumping fluid to maintain a stable core temperature. Because the battery is so sensitive to temperature, freezing weather outside will drain your range. Running the internal cabin heater pulls energy from this exact same vault, draining your driving distance even faster. The battery is an active, highly sensitive structural component. It dictates the car's physical agility on the road and sets the absolute limits of how far you can drive on a single charge. The energy resting in that floor vault is in the wrong format to spin the tires. This is component 3, the inverter. Acting as a translator between the battery and motor, it takes static direct current from the battery and converts it into alternating current, or AC. This reversing current is required to create a rotating magnetic field. That translated AC energy flows straight into component 4, the electric motor, which is mounted directly on the vehicle's axles. In a standard car, the engine has to spin up, send power through a multi-gear transmission, and wait for the physical gears to catch. Electric vehicles eliminate that step entirely with a single-speed setup. The result is instant torque. With no gears to shift, the motor spins up and the vehicle moves the exact millisecond you press the pedal. Removing the mechanical delay of shifting gears makes the vehicle perfectly responsive. The car becomes a direct extension of your foot. Now, step 5 takes effect during deceleration. Imagine driving at highway speeds and simply lifting your foot off the accelerator pedal. This triggers component 5, regenerative braking. The electric motor instantly stops consuming energy from the battery and transforms into a working generator. The forward momentum forces the generator to spin, resisting the wheel's motion to slow the car while capturing kinetic energy. This recaptured electricity is pushed backward through the inverter and deposited directly back into the battery vault. Combustion engines waste their braking energy by turning it into useless heat through friction. By capturing and reusing that momentum, this closed-loop system makes the electric powertrain vastly more efficient. We now have a complete circuit. The car pulls grid power from the charger, stores it in the floor vault, translates it through the inverter, spins the gearless motor, and recycles the momentum right back into the battery. This is an elegant, solid-state energy loop. It replaces the thousands of vibrating, degrading, and constantly combusting moving parts required to make a traditional gas engine work. By tracing this path, you have successfully built a working, end-to-end mental model of electric vehicle architecture. Now it is time to take this blueprint into the physical world. Go test drive an electric vehicle to feel the instant torque for yourself. If you have any questions about these 5 components, let me know in the comments below.